This section is about planes and their parametric and Cartesian forms and using vectors. So for a line, we take a point and we add on a parameter times a direction vector. To define a plane, we need two direction vectors, B and C, and we need a multiple of each one of those added to some given point in that plane. N is what we call the normal to the plane. It is the cross product of the two directional vectors, and N is always going to be perpendicular to the plane because the two vectors B and C are in the plane, and the cross product always finds something perpendicular to those two vectors. So what that means is that if we have any vector in the plane, call it AR, if we take the dot product of that vector with N, we'll get 0 because they're perpendicular. Dot product equal to 0 means perpendicularity. We can use this idea to get the Cartesian form of a plane, which would be AX plus BY plus CZ equals D, where A, B, C, and D are real numbers. So I want to find the Cartesian form for the plane with this normal and containing that point. So the first thing we do is we look at what vector AR would be, where R is considered to be X, Y, Z. So AR will be X plus 1, Y minus 2, Z minus 4. We can take the dot product being equal to 0 to write our equation. We take the dot product, it's equal to 0, so we get X plus 1 plus 2Y minus 4 plus 3Z minus 12 equals 0. Rearranging this, we get X plus 2Y plus 3Z equals 15. One thing to notice is that the coefficients here, 1x, 2y, 3z, those match up precisely with our normal vector, and that is not a coincidence. That always does happen. Here we have 3 points, A, B, and C. We want to write a vector equation for the plane that contains these points. We're going to start by writing down any two direction vectors that we want. I'm going to pick AB and AC. So B minus A, that's going to be 4, negative 1, 1. Then for AC, we're going to do C minus A. 1 minus negative 1 is 2. Negative 2, 3. Our vector equation will be some point, and I'm saying use A, but it doesn't really matter. Negative 1, 2, 0, plus lambda times the first direction vector, plus mu times the second direction vector. There's our vector equation for this plane. Now we want to write this equation in Cartesian form. To do that, we need a normal to this plane. And the normal is defined as being the cross product between any two vectors in that plane. We're going to use those two directional vectors. The way we find cross product is we find the determinant of a 3 by 3 matrix that's made up of I, j, and k, and then the two direction vectors. The first direction vector being 4, negative 1, 1. The second direction vector was 2, negative 2, 3. These are coming right from that vector equation that we wrote for the plane. And this cross product definition is in your notes packet, as is how to find this 3 by 3 determinant. But it's going to be I times negative 3 plus 2 minus j times 12 minus 2 plus k times negative 8 plus 2. So our normal can be written in vector form as negative 1, negative 10, negative 6. Now the problem is just like what we did in the first example. We need to find, we've got one of our points, we want to write vector AR. So that's going to be x plus 1, y minus 2, z. Now we want to take the dot product of that with the normal. And we know that this is equal to 0 because they are perpendicular. And we end up with negative x minus 1 minus 10y plus 20 minus 6z equals 0. Or rearranged, our Cartesian equation becomes x plus 10y plus 6z equals 19. In this next example, we have 2 points. We want to find the equation of the line that goes through them, and we also want to know where this line intersects the plane given by x minus 2y plus 3z equals 26. We're going to start this out by finding the parametric form of this equation. And we're going to take some point on the line, negative 1, 2, 3, this is the vector equation, plus our parameter t, and then we need the direction vector. And the direction vector that I'm going to use is AB. And AB is going to be 3, negative 2, negative 6. And what we can pull from this is that x is equal to negative 1 plus 3t, y is equal to 2 minus 2t, and z is equal to 3 minus 6t. To figure out where this line intersects this plane, we're going to take each one of those parametric values and substitute them in. So where it says x, I'm going to put negative 1 plus 3t. Minus 2 times 2 minus 2t. Plus 3 times 3 minus 6t equals 26. I'm going to solve this equation for t, and I end up getting t equals 3. Now I can take that t value and I can plug it back into my parameters and get x equals negative 1 plus 3 times 3 . I made a mistake. T does not equal 3. I was looking at the wrong part of my notes. T is equal to negative 2 for this problem. So I get negative 1 plus 3 times negative 2, which is negative 7. Y is equal to 2 minus 2 times negative 2, which is equal to 6. And substituting negative 2 into z up above, we get 3 minus 6 times negative 2, or 15. So the place that that line intersects the plane is negative 7, 6, 15. we're able to use the parameter t equals -2 to find where x, y, and z match up on this plane. To find the foot n of the normal vector from the point A to the plane will allow us to find the shortest distance from A to the plane. Shortest distance is always perpendicular. That's why we need the normal here. And I can take the normal by knowing the Cartesian form of the plane. The normal, at least the direction of the normal, will be 1, -1, 2. Remember, the normal comes from the coefficients in our Cartesian form. This is the direction of vector A sub n. Vector an can be given by the parametric form 2, -1, 3 plus t times 1, -1, 2. And we can, this would actually be line an. And we find that x is 2 minus t, y is -1 minus t, and z is 3 plus 2t. This problem is like the previous one. I have a plane. I want to know where this line intersects it. So I'm going to plug in 2 minus t for x minus -1 minus t for y plus 2 times 3 plus 2t for z equals 27. And solving this, I can find that t is equal to 3. And from there, I can substitute back into my 3 parameters and find out that n would be the point 5, -4, 9. Which means that an vector an will be equal to 5 minus 2 is 3, -4 minus -1 is -3, and 9 minus 3 is 6. The magnitude of an, i.e. the perpendicular distance from the plane to point A, will just be the magnitude of this vector. So it's exactly the square root of 54 units. And here are some problems that you can work on.